Thank you, Helen, for the in-depth market insight and analysis. I think our next speaker may have the distinction of traveling the furthest to be with us today, and we certainly appreciate that. It's my pleasure to introduce one of Inside's newest partners. You may have heard that Inside and TI are working together to bring UEFI firmware to the TI ARM-based OMAP platforms. From Dallas, Texas, please welcome the General Manager of TI's OMAP mobile computing business, Mr. Deepu Talla.
Thank you for the introduction, Stephen. Good afternoon, everybody. And I did not realize that I was the farthest, although I feel like Dallas is pretty close to Taipei because I'm here every month. So it's not that far for me. I want to thank Inside for the opportunity for me to speak today on behalf of Texas Instruments and the OMAP business unit. Many of you know Texas Instruments probably as an analog company nowadays. OMAP is one of probably the biggest secrets inside of Texas Instruments. And OMAP is our application processor business. It stands for Open Multimedia Application Processor. And earlier this year, in the first quarter, we actually announced that we have shipped 250 million OMAPs already in the last 10 years. And probably many of you do not know, but many of the latest and greatest smartphones and even tablets are powered today by OMAP technology. How many of you in this room, by a show of hands, own a smartphone and a tablet and a notebook? Okay, I think I see some of my friends at Microsoft and Intel, and including myself, feel very happy because there's a lot of opportunity to sell more SoCs and chips to you in this room and then many more. Did you know that OMAP is in the largest selling Android tablet today? Many folks look at a lot of the dual-core tablets, but the biggest selling Android tablet today so far has been the Barnes & Noble Nook Color. That has shipped in several million units, and OMAP has been powering that for more than a year now. Some of the recent product announcements that came out on OMAP technology include the Amazon Kindle Fire tablet based on our OMAP 4 dual-core Cortex-A9 technology. You've also seen Google and Samsung announce Ice Cream Sandwich, which is Android 4.0, and that's based on OMAP 4460, which is going to come to the market very soon. Also, the world's thinnest LTE phone from Motorola, the Motorola Droid Razr, is on OMAP 4. Also, Droid Bionic, one of the best phones on the Verizon network in the US, is based on OMAP 4. And the world's thinnest tablet to date, which Toshiba announced in September, is also based on OMAP 4. So we're one of the, like I said, the best kept secrets inside TI, but we are powering a lot of unique and latest and greatest smartphones and tablets. What I'm going to talk today is take a little bit of a different approach from the rest of the speakers in this. I actually thank Insight for putting me later in the presentation because all of the presentations have explained about where the tablet market is going, where the computing market is going, how CPUs are evolving, how graphics processors are evolving, how all these things come together and solve the mobile computing. I'm going to take it a step further and talk a lot about the system on a chip aspect of mobile computing. So if you look at it today, everybody has a smartphone pretty much in this room, right? There are 4 things that make a smartphone a must for everyone. The first one is it's always on. It's 24-hour battery life. You charge it in the night, you wake up in the morning, you do all of your day tasks, and you don't charge it until you go back to bed. Although, I must say, in some cases, Apple and sometimes Android, depending on how much use you make, you have to charge it maybe in the middle of the day. But nevertheless, the concept is that it's always on, 24-hour battery life. The second one is it's instant on. You press a button, within a fraction of a second, you're ready to do your task, whether it's making a phone call, whether it's doing your email, connecting to the web, whatever it is. The third one is it's always connected, whether it's connected to the cellular network, Wi-Fi, Bluetooth, GPS, sensors, whatever it is to the environment, it's always connected. And the fourth and last but not the least is it's always there with you. That's what makes smartphone a must-have device for everyone on this planet. Now you go to the other extreme and look at computing from a notebook perspective. Think about where notebooks are today. Very useful. Everybody has a notebook here in this room. But think about from an always-on perspective. It's definitely not always on. It's sometimes on. It's on for 3 hours at most, typically on most batteries, before you need to charge it. Think about instant on. It's definitely not instant on. You press a button, it takes several seconds, and in some cases from a cold boot, you're talking about minutes before you cold boot. It's sometimes connected through Wi-Fi maybe, right? So, and you think about tablets, they're in the middle. What the users are expecting as we move forward is a consistent user experience across all of these domains. Whether it's a smartphone, whether it's a tablet, whether it's a laptop, the users are expecting the same consistent experience. Now, if you look at how silicon vendors such as TI are approaching the problem, we come from the smartphone world, now we are going up into the tablet world and the thin laptop world. And for us, it's the same. By that I mean, in terms of what we're trying to do, it's the same approach, whether it's a smartphone, whether it's a tablet, whether it's a thin laptop. The only thing that the user cares about is what is the display size, what's the battery size. But in terms of user experience, it needs to be always on, instant on, always connected. Now, in order to do that, and I will show you through the later in the presentation, it is not enough to do all of this computation on a CPU and GPU that we are used to for the last 20, 30 years. That delivers a battery life of 3 hours. That does not deliver a battery life of 24 hours. That delivers a multimedia experience that is barely 1080p. So I'm going to show you that in order to get to the right user experience, we need to do beyond CPU, GPU. It is going to be about the full SoC. And if you look at from an operating system perspective, different vendors are approaching it differently. You look at Microsoft. Microsoft has announced Windows 8 at the beginning of this year at CES, and TI OMAP is one of the ARM vendors that Windows 8 will be ported onto, or is being ported onto right now. And you look at the vision there. Tablets or notebooks or anything else, it's the same consistent user experience. Now you look at what Google has done with Android, especially with Ice Cream Sandwich with Android 4.0, smartphones and tablets have the same operating system. You look at what Apple has done with the iPhone and the iPad, it's the same operating system on the phone and the pad. Now, it's only a matter of time before we can expect that's the same operating system and same underlying software that's running on a phone or a tablet or a laptop. It's just a matter of time. Okay. So some of the applications that I will talk about here, these are, I took some examples as to how an OMAP processor solves these problems in the right battery life. And by right battery life, I mean whether it's a phone or a tablet or a thin laptop, delivering great user experience, uncompromised user experience in a battery-operated mode, and you need to deliver a 24-hour user experience overall. So today, OMAP 4 is shipping in many products. OMAP 4430 is our first generation dual Cortex A9 1 gigahertz processor. And OMAP 4460 is starting to ship now, which is our next generation. That's the Ice Cream Sandwich lead platform. And we also have an OMAP 4470 that's coming for next year in our roadmap. And then OMAP 5 is going to sample very soon, later this year, and it's going to come into production for second half of next year. And OMAP 5 actually is going to be the industry's first ARM Cortex A15 mobile processor. And I'm going to take some examples in the later slides using both of these processors and show you how these applications are mapped onto the processor. And by processor or SoC, I mean not just CPU and GPU, but all the other components. And that's what I'll prove to you that it will lead to the best user experience possible. So we'll talk about computational photography, augmented reality, mobile security, advanced UIs, gesture projection, and also HD video conferencing. So let me deep dive into, before I deep dive into those applications, let me give you a flavor for what is inside this OMAP processor. And I apologize, I don't think any one of you can read this, what's inside here. But this is a SoC. This is a OMAP 5 block diagram. First thing we have, CPUs are definitely one of the most important blocks inside a SoC because that's where you're running your high-level operating system. That's where you're running your web browser. That's where you're running any of your general-purpose processing on the CPU. So we have, in this case, dual Cortex-A15s running up to 2 gigahertz each. In addition to the CPUs, we have multi-core graphics. In this case, we have, with our partner Imagination, we have SGX 544 multi-core graphics engine. So that's where the comparison between a SoC, as it's a mobile SoC, and general-purpose APUs or CPUs end, because everybody has CPUs and GPUs. But here in SoC, we have many more blocks. And it's, to give you a rough idea of what I'm talking about, a CPU and GPU, in the case of OMAP, roughly take up maybe 50% of the die size. So that gives you a flavor for how much more acceleration we're putting in some of the other blocks. And some of the other blocks include video processing. We have a dedicated engine for video processing. Actually, pretty much almost all of the mobile SoCs today have dedicated video engines. These are for video encode, video decode, video transcode. Again, every SoC vendor has, depending on what the capability is, in some cases 720p, some cases 1080p. We have going all the way up to 1080p, 60 frames per second. So anytime you're playing a movie, capturing a video, none of the CPU or GPU is used. Everything is offloaded onto the video accelerator. We have imaging and vision accelerators. And in the case of imaging and vision, it's not about just supporting one camera. In the case of OMAPs, we support up to 3 to 4 cameras in parallel. You might ask, why do you need 3 cameras? There's a good example today. So there are phones released in the market today with OMAP, LG Optimus 3D, which is the first full HD 720p capture and decode 720p stereoscopic video phone. So when you have a tablet or a phone with 2 cameras recording stereo and then for video conferencing on the other side, you can see that there are 3 cameras needed. Now, moving forward, you can imagine cameras being used not just for taking a picture or video, but you can use one of the cameras to capture an image or video which is not for human consumption directly, but it's being used for, whether it's for gesturing, whether it's for augmented reality, where it's consumed by the user in a different way. So from that standpoint, it's important to support multiple cameras in a system. So when you're supporting multiple cameras, it's important to be doing all of that processing in an extremely low power, low latency way. And so those tasks are not for CPU or GPU. So those are for hardware accelerators and programmable accelerators. So we have many programmable accelerators for imaging and vision in the case of OMAP 5. And this block diagram doesn't show you all the details here, but to give you a flavor, it is multiple cores of SIMD cores, multiple DSPs, multiple processors, some in hardware, some programmable. DSP. In the case of OMAP, we have VLIW DSP, which in itself is multi-issue, 4-issue or 8-issue instructions per cycle, and doing many of the fundamental DSP tasks, offloading the main CPU and GPU. 3D graphics, of course, I mentioned. Everybody has a 3D graphics core. It's very important that 3D graphics is used not only for the graphics function, but also, as you've heard in the earlier presentations, GPU or the general purpose GPU for direct compute or OpenCL. We also have a separate 2D graphics engine wherein we can offload the 3D graphics for 2D UI composition done at a much lower power and a high performance. Display subsystem. This actually is a very big differentiator for us in OMAP. We can support up to 4 displays in parallel on OMAP 5. In the case of OMAP 4, which is currently shipping, we have demonstrated we can support 3 displays in parallel. You can ask, why do you need 3 displays? But think about a scenario where you have your tablet. You're using, let's say, 1024 by 600 or a 1280 by 800 display on the tablet. You go to your office. You're able to dock it. And you're powering your WUXGA monitor, which is a 1920 by 1200 monitor. So right there, you have 2 screens. And then you can also stream a 1080p movie through HDMI. So these are kind of the use cases that are going to become very popular very soon, which means that the amount of computations that you need to be able to do in this SoCs is significant. So it is, and actually, if you look at PC processors today, none of the PC processors can do a 1080p movie plus a web browser plus HDMI, all of those simultaneously. And the reason being, they're not accelerated. Okay, if you accelerate all of these, you can do them at extremely low power. And the power consumption that I'm talking about in doing all of these use cases is still under a watt on the application processor plus memory. That's the power of SoC. Okay. So in the case of display, we can support up to 3 or 4 displays. Now imagine when you're doing displays, rarely do you just throw video. Many times you need to do composition, you need to do picture-in-picture, you need to do graphics overlay along with the display. Now, typically what happens is most of the time that sort of composition is done in the 3D graphics engine. That's okay if you're doing 1 screen. But what if you're doing 3 screens? Would you spend all your graphics on doing just composition? Now what happens if you want to run a 3D game in parallel? You can. So you need a very powerful display processor. So in the case of OMAP, we have an embedded display processor. Security is a very important element. And earlier in the presentation, Tony from Microsoft mentioned about the TPM and the amount of security that's going into Windows 8. And we are leveraging our security subsystem completely embedded inside OMAP without the need for an external chip to run the full Windows 8 functionality. Okay. So the other difference that you'll also see is in the case of OMAP, I mentioned we can do multiple cameras, we can do multiple displays, we can support multiple sensors, which means you're running multiple screens with many sensors, image sensors, displays, and so on. Now, imagine you're running your high-level operating system on your main CPU. You're running a 3D game on your graphics engine. How do you control all the image sensors for autofocus, auto exposure, auto white balance, and face detection, face recognition, many other functions? Try using a main CPU with a high-level operating system to control all of those. You will be running into many interrupts. You will not have the right latency. So what we have done is we have embedded real-time microcontrollers inside the OMAP. Last week, actually, ARM has announced what they call a big little approach moving forward with Cortex A15 and Cortex A7, wherein the idea is that when you're running high performance, you run it on the high performance CPU. When you need to go into low power mode, you offload from the high performance CPU and to run it on the low power CPU. In essence, that is what we're doing already here today in OMAP 4 and OMAP 5, where we are moving the real-time functions for imaging, for video, for security, and so on, for display, onto the lower power ARM microcontrollers, freeing up the main CPU to run the main operating system and web browser, and so on. So what this does is, when you're running multi-screen applications, when you're running a high-level operating system, running a game, running a web browser, running a video, running imaging, all of these tasks are partitioned onto the SoC on different hardware processing blocks, which is the only way you can run all of these things in parallel. And again, like I mentioned earlier, it is very important to run all of these in a very low power budget. A smartphone budget, thermal budget, or a power budget is not going to grow. It is still in the range of 1 watt to 2 watts at most for the peak thermal. In the case of a tablet, it's not going to go beyond a 3 watt or a 4 watt. So you need to be able to deliver the right level of user experience within that power budget. And the only way to do that is not to rely purely on CPU and GPU, but to balance the full system, running it on the different accelerators. Okay, so I'm going to skip this slide, but this is essentially the OMAP 4470, which is the OMAP 4 version, very similar concept to the block diagram that I explained earlier. Okay, so now let's jump into video conferencing. Video conferencing has been there for many years. It's becoming increasingly popular. Many people today use Skype. And actually, earlier at Computex this year in Taiwan, we demonstrated a full HD Skype running at 300 milliwatts on OMAP 4 processor. Now, when you're doing video conferencing, there are many things that people think of. First thing is you need to be able to do a video encode. You need to be able to do a video decode. These are fundamental. Everybody can do that. Now, the question is, what is the power budget? What is the latency you're able to do that in? What is the interoperability? That is very important. Apple FaceTime is very interesting, but it is only Apple to Apple. Okay, what if your family member is on the other side using a PC with a certain client, and on the other side you are using your latest and greatest Android phone with a much more capability? How do you video conference across those? They're not the same capabilities on both sides, but you want to deliver the best user experience on both sides. So in order to do that, you need to be able to deliver a compelling user experience. And how do we do that on OMAP 4 today, or OMAP 5 for that matter? First of all, you need to be able to deliver high definition quality, because your PC screens are high definition, your smartphone screens today with the Android 4.0 ice cream sandwich is a full 720p screen. Your tablet screens are already at 1280, 800, soon expected to go to 2K by 1500 resolution, maybe even go up to 2.5K by 2K resolution in the next year or two. So when you're at that resolution, you need to be able to deliver HD user experience. So simultaneous 1080p encode and decode is required. Okay. So this function cannot be done on CPU. Today, try to play a 1080p Blu-ray DVD on your notebook, open up the Windows Task Manager, and look at how much CPU is left. Pretty much, you'll be lucky to see any CPU MIPS left to do anything. That's because everything is running on the CPU. But in the case of SoC, CPU is not at all utilized. When we're doing this function, the CPU is utilized less than 1% of the time. Everything else is offloaded onto the video accelerators. So the video accelerators on OMAP 4 can simultaneously do a 1080p encode and a 1080p decode at a budget of 400 milliwatts. This is a 400 milliwatts for the complete system on a chip. Now think about that versus your PCs that are taking 30 watts to 40 watts. So we're talking about 2 orders of magnitude power reduction. So in addition to being able to do the HD encode and decode, you're capturing your own image to encode, which means you require to do a very good job of the image processing to make sure that the quality of the video is very good. So we have a full function image signal processor embedded inside OMAP, doing high ISO noise filter. This is, most of the time when you're doing video conferencing, you're stuck in a low light environment. You're sitting in your living room, you're sitting in your, on your couch, or you're sitting in your office where the lighting is not the best. So in order to do a very good video quality, you need to have a lot of image processing done to make sure that the end video quality is very good, because you're talking HD resolution at this point. Sharpness, color, distortion correction. So all of this is done on the image signal processor block. Again, no CPU, no GPU. Okay. We need to support very low bit rate. If there is wireless LAN access, typically you can get multi megabytes per second. So you can do maybe get away with a couple of megabytes per second. But in most cases, you are on your 3G or LTE. And now with data bandwidth being an issue and also the data capacity being an issue, it is very important to do this sort of 1080p encode and decode under a megabit per second at high quality. And we are able to deliver that because we have algorithms inside our DSP that we are leveraging to reduce the bit rate. Latency, of course, is very, very important. You need to be able to see real-time what's going on the other side. So typically a 1 or 2 frame delay is acceptable, not a 10 frame delay, which means you need to be able to be using techniques that are used in professional video conferencing systems like slice-based video encoding, H.241 standard, and so on and so forth. So we do all of those. Of course, I talked about the low power aspect of it. You need to be able to do, you're still doing this on your phone or your tablet. The battery life is fixed, and you need to be able to deliver continuous user experience for multiple hours. So it needs to be in the hundreds of milliwatt, not in the tens of watts. And of course, with moving forward with video conferencing, there is a multi-party video conferencing that we showed actually even at Computex earlier, which is ability to act as, one of the tablets acts as a bridge, meaning there's 4 parties that are doing video conferencing, and without an external bridge, everything is being controlled by one tablet. So in order to do that, you need to be able to decode multiple videos. In this picture, you see 6 parties that are conferencing. And you would want to potentially substitute the background. Earlier, one of the speakers mentioned avatars are becoming popular. So any of those capabilities can be done. So that's where you would traditionally use your GPU potentially to do blending or composition, or your display subsystem to do that. And one of the things that is we do consciously is work with a lot of partners in the industry. We try to do many things internally, but also try to leverage the experts in the industry. So in the case of video conferencing, these names are very familiar. Polycom, Actually, if you open up any of the Polycom or Cisco Tandberg higher-end enterprise systems, these are all powered by TI DSP today. We've been doing that for the last 10 years. So we have built the know-how in how to do video conferencing at low bitrate, low power for 10 plus years. So Skype, Polycom examples, Radvision, ETM, Google Talk. So we leverage, work with all of these ecosystem partners, use their frameworks, and port it onto the OMAP platform to deliver this level of user experience. Now, it is entirely possible that if you're in a multi-screen environment, you're using one screen to do the video conferencing, and you still need to do your web browser on the other screen, or you still need to run your Office on the other screen, where you're doing a PowerPoint. So in that case, the CPU is used for your web browser or for your Office, but the CPU is not used for any of this function. So this is only, again, possible to do with SoC. Okay, next is computational photography. This is actually gaining more and more prominence as seen, probably some of you have seen when Google announced the ice cream sandwich Android 4.0, they talked about many features, some of which include face detection and also many camera features such as simultaneously capturing a 1080p video and being able to take 5 megapixels without switching between video and imaging modes. So there's a lot of those kind of functionalities that are going to become popular as we go into smartphones, and smartphones eventually become good enough or can be delivering a similar quality of a picture and user experience as a high-end still camera. Maybe not a digital still, not a DSLR, but close to a high-end digital still camera. So in order to do that, we need to be able to support high resolution. Today, it's 5 megapixel, 8 megapixel, going to 12 megapixels, and like I mentioned, in some cases, stereoscopic video, stereoscopic pictures, which means 2 12 megapixel cameras. So in order to do that, you need to be able to have a high-performance ISP. Hardware face detection. So OMAP actually has embedded hardware face detection today. So we do hardware face detection up to 30 faces at 30 frames per second real time in single-digit milliwatts using that hardware face detection engine. So it essentially is a free function but at the end of the day, the user gets a tremendous amount of experience by being able to access the face, recognizing the face, but done at almost free power budget. And of course, when you're doing the computational photography, the quality of the video, the quality of the pictures needs to be extremely high. So all of this is, again, accelerated on our image signal processors, with our SIMD accelerators, with our DSPs, with our processing blocks, not done on CPU or GPU. Okay. Again, system-level optimizations as we're working with Google, as we're working with Microsoft and other operating system vendors to make sure that all of these functions are brought to a higher level of abstraction, where not only does TI software work on this, but our ecosystem partners that are developing software and applications at the Android level or at the Windows level can leverage these accelerators. That is a very fundamental point, because it's easy to build a lot of accelerators, but it's extremely hard for software to use them effectively. Okay, this has been the problem in the computing industry for the last 30 years, wherein we have gone multi-cores, multi-gigahertz, but the problem has been how do you keep the cores busy, because software does not port well. So that's been one of the biggest challenges that we're working not only at TI, but through industry partners and working with on APIs, working with ecosystem partners to make sure that these hardware accelerators are utilized very well in software. Because at the end of the day, if the software applications cannot use the hardware accelerators, it doesn't matter. Okay. Computer vision optimized APIs, this is the one that I mentioned, which is where we are making sure that the complexity of the accelerators are abstracted from the software developer. So when a software developer develops to the Android framework, he does not, or a Windows framework, they do not need to know that whether it's a CPU, whether it's a GPU, whether it's a DSP, whether it's an audio processor or image processor or display processor that is mapped onto. They just program in HTML5, they program in the Android API, but we, with our BSP and with our app layer, we make sure that we translate that application into these accelerators. So from a user perspective, they get the performance, everything transparently. Okay, so again, these are some of the partners that we are working in enabling computational photography. Augmented reality. This has picked up a lot of steam in the last 12 months, and this we think will continue to grow. And in order to do augmented reality, this is actually a very challenging task because, because when you're doing augmented reality, this is typically going on in parallel with some other function. You need to do this without taking away CPU MIPS or GPU MIPS and doing it at extremely low power, because this is one of the classic background tasks. Because all the user sees at the end of the day is you're pointing your camera at a particular picture, and that your picture or whatever the picture you're looking at there is replaced with some other picture. That's the end effect. But in order to do all the computation in the background, there's a lot of computation that goes on, including capturing the picture, processing the picture, doing data mining, figuring out whether you send it to the cloud or you do some local processing on what the picture is. It could be sometimes in a 3D object. You need to generate different rendering. So all of this needs to happen in the background at a very low power. And in order to do that, you need to make sure that you have a balanced architecture beyond a CPU and GPU. Okay. Advanced UI. So high-resolution multi-display support, I mentioned today in OMAP 4, we support 3 displays in parallel. We can support a WUXGA display, which is a 1920 by 1200, in parallel to a 1080p movie, in parallel to a WXGA display. So those 3 displays can be done in parallel. In the case of OMAP 5, we can support 4 displays in parallel. So the classic scenario again here is when you're using your smartphone tablet in a single mode, you're only doing 1 display. But when you're taking your smartphone and tomorrow you're going to do wireless HD or Wi-Fi direct or any of the scenarios where you're streaming content from your phone or your tablet to your TV wirelessly, you're supporting essentially 2 displays. And when you're docking your smartphone or tablet and you're powering 2 screens, then in that case it becomes 3 displays. So you need to have the computational capability to handle multiple displays. Of course, one of the most important thing when you're doing these multiple displays is having the right amount of bandwidth. And that's fundamentally one of the biggest advantages of our OMAP approach compared to our competition is today we provide the highest DRAM, low-power DDR bandwidth in the industry. Since the beginning of this year, we've been supporting 6.4 gigabytes per second. That allows us to do multi-screen at very low power. Also, I mentioned that in the case of display, we are able to, this display processor is very flexible. It can blend videos, blend graphics without requiring the GPU MIPS. I'll give you one example. If you look at Adobe Flash today and try to play a 1080p movie in an Adobe Flash environment, you run that on your PC today. You open up your PC and you run Adobe Flash 1080p and open up your Windows Task Manager. You will typically see a dual-core Core i5, probably around 70% loaded to do that function. Now you move that to mobile SoC. There are 2 big time-consuming tasks when you're doing a 1080p Flash. One is the 1080p video decode itself. And we talked about that all mobile SoCs nowadays have a video decoder in hardware. So you offload the video decoder onto hardware. But that's only one of the big computational tasks. The other big computational task is you need to do the color conversion, you need to do the composition, you need to do scaling, you need to do rotation. Typically, all of those are done. In the case of your traditional PC, everything is done on CPU. In the case of mobile SoC, it's done either on CPU or on GPU. In the case of OMAP, as the BlackBerry playbook, which is also based on OMAP 4, has proven, we offload the complete color composition, color scaling, rotation, and all of the other functions that are associated with the Adobe 1080p Flash onto the display subsystem. So when you are playing a 1080p Adobe Flash on a BlackBerry playbook, your CPU is loaded less than 3% of the time. Your GPU is 100% free. So which means that we are able to demonstrate Adobe Flash 1080p in 200 to 300 milliwatts, which is a significant user benefit that you cannot get with any PC type of device today. Okay. So I also mentioned that in addition to a 3D graphics engine, which is very important for 3D gaming, important for composition, we We also have a 2D graphics engine, which is heavily used for us in 2D scenarios. Why spend a 3D graphics core when you don't need a 3D graphics core? So we have a 2D graphics core. And I also mentioned that in order to do some of these applications, we have face detection, face recognition, all of those in hardware. And again, in this case, we have several partners that we're working with to enable advanced UI on OMAP. Okay, this is my last slide. In the case of mobile security, I mentioned, we are working with Microsoft on Windows 8. And today, if you open up your PC or your notebook, you typically have an external TPM chip wherein that's doing all of your security. In the case of OMAP, everything is embedded inside the OMAP SoC. We don't need an external solution. We are able to do that because we have what we call the M-Shield security, which is beyond the ARM trust zone. So ARM has a great solution in trust zone, but that's only related to the CPU piece of it. We have what's called M-Shield, where every block inside OMAP, whether it's a small peripheral or any memory region, you can specify if it is secure or not. And if it say it's secure, that content is only accessed by that process ID. Okay, so which is guaranteeing that no other process can come in and take over that content. And we are leveraging that technique today. So the Motorola Droid Razr that was launched 2 weeks ago is actually the first and only mobile device that can support full Netflix HD streaming. Now, everybody can do SD streaming, but in order to do HD streaming, there's a lot of security processing that needs to be done, and you cannot do that in software. That's why only OMAP is capable, because we're able to offload everything to hardware, and there's not enough CPU MIPS to do it in software. If you do it on software, of course, you need the CPU is taken up, number one, and number two, importantly, the power consumption is going to be extremely high. So we do all of that in hardware. So we use our M-Shield security system to do all of the secure processing in hardware. So all of the cryptographic accelerators are also embedded inside the hardware inside OMAP 4 or OMAP 5. And also we provide full private and public keys. Okay. And so some of the partners that we're working with, Gemalto, and of course we're working with Inside on UEFI as our lead partner for Windows 8. Okay. With that, I'd like to thank you for your time.